Scalar measurements are often affected by errors. This context yields uncertain scalar fields, where each point of the domain is now mapped to a probability density function. This example shows the velocity of the uncertain Kármán vortex street. In this work, we introduce new algorithms to extract the common topological denominator of all possible realizations of the input uncertain data. In particular, our algorithm extracts mandatory critical points, defined by a region of the domain and a function interval. For each of these, at least one critical point has to happen in any realization created from the input data. The function interval prediction can be used to drive an opacity transfer function, which denotes the positional uncertainty of the critical points within these regions. Our core algorithm is based on the simultaneous analysis of the scalar fields that describe reliable estimations of the bounds of the support of the probability density functions of the input, as further described in the paper. The global nature of this algorithm enables to construct mandatory, join, and split trees, which describe the global relation of the mandatory critical points. In the trees, the critical points are represented by vertical bars, describing the function value uncertainty of these features. These trees can be used for an interactive exploration of the data, as showcased in this example where the user interactively selects the features to display. Moreover, our approach also allows for progressive cancellation of the mandatory critical points, which enables to reveal the most dominant features of the data. Our technique can also be used with traditional scalar fields with a known error bound. This example shows an acquisition of the ground elevation on Mars with an error bound of 40 meters per vertex, which is 1% of the global function range. Here, the user interactively explores the structure of the most dominant craters, represented by mandatory minima, as well as the structure of the rims of nested craters, here represented by a mandatory saddle. This example shows the uncertain sea surface height obtained from 31 observation datasets. The mandatory extrema reveal the relation between sea surface height and well-known streams around the globe. The Gulf Stream in the Atlantic Ocean, along the southwest coast of Australia, or South Africa. The visualization of the mandatory saddles enables to apprehend the relations between these extrema. The importance of the streams is emphasized with a progressive simplification, since extrema are maintained in these locations after simplification. Even when the observations have little common features, our analysis still manages to extract their common denominator. Here's a challenging example for our technique. It represents the velocity of the flow generated by a heat source with various viscosity parameters, yielding a very unstable flow trajectory. Our technique still identifies several mandatory critical points, including a dominant maximum that describes the cone through which the flow will travel for any realization of the input observations. In contrast to previous numerical techniques, our approach is purely combinatorial and does not depend on any parameter. Moreover, its global nature guarantees a global consistency of the computed structures. In particular, given a certain scalar field with prescribed error bounds, the mandatory join and split trees match the certain ones as the error decreases. Also, the time complexity of our algorithm is output sensitive, which makes it well suited for ensembled datasets. The prediction accuracy of our analysis is further demonstrated in the paper with thorough verification experiments. In conclusion, our approach allows for an efficient and interactive exploration of the mandatory topological structures in uncertain scalar fields, which helps the users to get deeper insights about their uncertain data.